So today move on then to talk about, I've put them on word here, but the decay processes of these excited states, the NO. And then the second part of the talk then will be about cold collisions involving Rydberg atoms. So the order of the Rydberg atoms molecule collision would be Rydberg helium atoms colliding. So just to recap where we were yesterday. So yesterday I showed you that we could excite these NO molecules and use this two-step laser excitation scheme. These Rydberg series converging to the lowest vibrational state of the ion. So when Rydberg states are excited, the ion that the Rydberg electron is bound to is not vibrating. And then we can access a few different rotational states. So depending on the Rydberg state we pick, the molecule of electron ion 4 could be rotating. Then the thing that will be interesting here is that there's this low n state, so the n equals 7 states of the first excited vibrational, or the series converging to the first excited vibrational state of the ion, but are very close in energy to this ionization. So this will have an effect on the lifetimes that we have. Then I showed you this behavior, so where we trap some molecules. In this case, they're say with n equals 38 and n plus the rotational constant 2. And then we trap them for about a millisecond, and we see that at early times there's a single exponential decay, so there's a log scale on the vertical axis, and then there's this sort of slower decay later. What we want to do is fit some exponential functions to this to extract some information about the decay processes from the trap. And they're not directly the lifetimes of Rydberg states. It could be that there's some field effects in the trap that are affecting it. So we're really looking at trap loss. It's sort of a proxy for lifetime. We have to at least be aware that there's this possibility. And then just to show you, we can trap this range of states. So this is after trapping time is 350 microseconds. We just scan the excitation layers to see what states can be trapped. And then this is this range of states. We want to look at then the lifetimes of states from states that the strong difference. Then I should put this in some context. So before we did these experiments, the longest lived Rydberg states of NO that we measured had lifetimes of around about a microsecond. And so these NF Rydberg states in this series with n equals 2. So between n equals 40 and n equals 70 in a lot of these experiments by Mark Fraction and ITAMP, where normally zero fields would stay estimated about 25 millivolts per centimeter, and the lifetimes are about 10 nanoseconds. So they apply the small fields. And the reason for these short lifetimes is that when the molecule is excited in the ground state, so this is supposed to be where the molecule is in its ground state, then you excite this Rydberg electron, and the charge of the Rydberg electron disturbs the bond of the molecule, and these low L states where the electron can interact or gets in close to the electron line, then this can lead to the molecule associated. So this happens quite fast. Along with timescales for these low and low. So in our experiments, we excite some of these states, and sometimes by the deceleration process, we filter out the molecules that have ended up in the longer lived state. So we're kind of, it's a bit of a trick in some way that we're not actually directly exciting these longer lived states. We're exciting some bunch of molecules, but there's some that get mixed into these longer lived states, and we filter them out. So actually, we have a big inefficiency in the number of molecules that get excited once we end up in the states we want, and then in this kind of example. But this is okay, looking for two possibilities. So then I return to this. So now we would like to measure by fitting something here, the decay rate. And we would expect then, or you would think that if these long-lived states, that they're kind of like on the time scale of the lifetime of Rydberg states in that. So you think that by going to these higher L or L mixed states, we've removed most of the molecular power. And if that's the case, then the lifetimes of a pure L state in an atomic scale is between N equals 3 and N equals 5. So the low L state scales to N equals 3, and if it's a circular state, it scales to N equals 5. And these L mixed start states that we excite, so these have a bit of many L character, and you can calculate, work out what the composition of the states are, and work out their lifetimes. So So these low M states that we said they're around about N. They should scale with around about N. So then we want to extract some information. So we see that we can't fit a function to this whole curve here. So what we do is we only fit this exponential decay to this part here in between 50 and 350. We don't fit the beginning part because there can be some oscillations that come off in the top and stop the top. So this sometimes gives a little bit skewed results here. And if we go for we fit for too long times, then this slower decay process is longer lived components that starts to play. So we take this region and put some tests where we make it short and longer and see that it doesn't disturb the decay. So we found it to be a reasonably range that the fit. We do this then for a range of different values of n. So like some bottom here is the wave number of the excitation later. And for the second step independent, but I've indicated the values of the principal quantity. Left to right. So if there's an half point decay, we would then or nominated by spontaneous emission, we would expect lifetime to increase as we increase n. We don't see this more. We see then a decrease from around about 400 microsecond lifetime. That's 10 is around 32 or 33, to about 250 or 220 microsecond lifetime around n. And what I've plotted here are just the lifetimes of the states in this Ender sequence. Then there's some kind of disturbances. So there's these states here at n equals 34 and 35 that have kind of different lifetimes to the ones around. And also there's a little bit of an increase here at 30, around 40 and here maybe 42. So when we try to understand what's going on. To understand this, we first compared what we would expect if these were really hydrogenic states. So we were just dealing with the fluorescence of these cells. So if these were states with n equal to 2, so if they had E higher, then the lower ends we expect to live for a few hundred microseconds, so we'll not quickly go up the measure. The higher ends we expect to live for 5. And if it was n equals 3 or 4, which is probably what the case is, we expect then a bit of a stronger increase from about 500 microseconds up to. This is completely not what we see. Then we have to think about what happens. So we have this other Rydberg state of this series converting to the excited vibrational state. This has a very short lifetime. So this has been measured by the line which has been measured by spectroscopy by two sources. Determined from the line with the lifetime of these states is around that 1 peak. In principle, they can decay by polarization, so they can decay into the continuum here. Then these series can be coupled. They're coupled because of the interaction of the Rydberg electron with the electric dipole moment and the dipole moment of the ion. And this dipole and dipole moments depend on the internuclear distance of the ion. And this means we're coupling between these two series of different vibrations. So this you can write down. It depends. So this is the interaction. This is something we take from this more trial. It depends on the sum of the different contributions to different states. It depends on the derivative of the quantum defect with respect to so we can estimate from this what this comes. So what we do as a very kind of simple model of this is we consider so the center of this quantum states is around about 100 centimeters above the lowest ionization threshold. So we consider just for a very simple picture to have a state that's 100 centimeters above this ionization, and that we say it has a width in the frequency domain that's the inverse of this 1%. So we have a Lorentzian function that has a very small amplitude out here, down at the energies of the states, higher or Rydberg states in the end. So then we think that, okay, the lifetimes of our Rydberg states should be then their fluorescence lifetime, or the decay rate, I should say, the fluorescence, decay rate because of fluorescence, which I write as this amplitude here, plus some small contribution from the decay rate because of this association, because it's coupling to this. And this is this very fast decay rate that corresponds to picosecond lifetime, so we only need a small contribution from this have an effect on the lifetimes based on the measure which are. So we do just a fitting procedure to see what should the amplitude of this Gaussian function be, or sorry, the Lorentzian function, if it gives, if we add then the small contribution from this fast decay rate to the lifetimes of our state, we add it to the first. And we find that we only need to factor in 10 to the 9 of this second decay rate to our very slow decay processes to get the kind of effect we see. So if we add then the calculated fluorescence lifetimes for these states to this small energy dependent contribution from the copper killer state, we see then a behavior that matches really well to what we see in terms of this then. So really what's happening is we're just adding this part in 10 to 9 of this very short-lived state, and it's causing a change in the lifetime of our reference state on the level of the filament or the behavior on the level of this changes a few microseconds. Because of this interaction in between these two. And so we can also estimate from this calculated coupling extent. So okay, here we just do something completely true. So we really just have this function that is the n dependence of the spontaneous emission rate. And then we choose some scaling factor, this absolute, that is then multiplied by this ecosecond. And then we just fit that to here, and then we find that we need to the scaling factor then gives us something that follows this decay if it's contribution to let's say it's parts of 10. Yeah. So but then we have done a kind of two level system estimation using this fraction, this coupling. And if we do this for our states, we also get something on the same scale within the same. So this is from Sir John calculated these distance dependent. So this is more just to give us an idea of that. But okay, this is experimental with simple model. So to do this properly, you should do this with something like that. This would then get the features are very small, so this would be hard to see in spectrum because these correspond to shifts of the energy levels. Because here we have this big sensitivity because of measurement. Okay. So first observation of these kinds of things. Okay, so that is our explanation of this general trend. So why do the lifetimes decrease as the increase? And then the other thing is that there are these sort of outliers. These all arise because there's interactions between the different rotational states in the Rydberg series that we're deciding to one converging to the lowest vibration state. So these places here that indicated to be black dots, where n equals 4 to 46 and 5. But these places, the Rydberg electron is coupling or causing the interaction of the Rydberg electron with the quadrupole moment of the ion core. There's a coupling between series with n plus equals 0 and n plus equals 2. So we end up exciting, for example, in this resonance, an n plus 2 state with n equals 40, and n plus equals 0 state with n equals 40. And they're both, the molecules in both of these states in the trap. And the n equals 44 state has a longer lifetime, and then it couples to this state with a shorter lifetime, or they're both there, so we see then a slight enhancement in the lifetime of this n. The same is true in this case, n equals 43. It's generated with the n plus equals 0 state. Then we see these shorter lifetimes here for these lower ends. This is because of the interaction of the Rydberg electron with the quadrupole moment of the ion core, so that leads to a coupling between rotation series that differ in rotational quantum number by 1. And so I haven't plotted these lines here, but at these positions there's this n equals 34 state in the n plus equals 2 series, and this degenerates with the n equals 32 state in the n plus equals 3 series. And this lower n state has a full lifetime, and then leads to this lower apparent decay rate from the trap. So that's where I make this caveat, is we're just measuring the decay rate of the things that are in the trap, so they're not directly like the individuals. In some cases they are. In some cases there's molecules in 2 different states. These are some examples. And then I should say so that these features that we see, they're not haven't been predicted. So there's work by Dixon and Dortner from the mid-90s where they looked at then these kind of overlapping resonances and to see where there would be effects. But in this paper, because then, or at that time, measurement lifetimes were only for lifetimes of the order of microseconds, it looked like it wasn't possible to see many of these effects. Didn't see them experimentally very long. This is then just the end of this first part. So we've mapped these molecules and these hydrogen-like Rydberg states. They have very long lifetimes, so as long as you would expect for atoms, but they still show some molecular effects. And because of this, the N scaling that you would consider for spontaneous emission now doesn't think about the details of other interactions with them. Now we are doing some follow-up experiments on this, so we're now exciting Rydberg states higher up in this B plus equals 1 series, and they can all ionize into this. So we want to look at effects of very slow ionization. And the last one with these states we can the molecules in this series that converge this excited vibration state. And this is kind of where we want to start to understand now in detail the contribution to the different processes. Are there any questions? The second part then is a bit different. Questions on this. Then I should say, so this is all, this part all about the capers is the PhD work that I'm doing. Okay, so then the second part connects, it's again at kind of Kelvin, a bit below Kelvin, but it connects a little bit more now to things with ultra-cold like dimers. So what we want to look at here is the collision of a helium Rydberg atom in the low L states, in the S Rydberg states, with an ammonia molecule in the ground. And we do these collisions at energy is a bit below Kelvin, so they and what we look at is this process of resonant energy transfer. So it's the same interaction that gives rise to the dipole blockade in Rydberg states, but here we're looking at this dipole-dipole interaction between the ground state molecule and the Rydberg atom. We still take advantage of the big electric dipole moment of the Rydberg states, but then we don't have the second collision part that doesn't have such. So the transition dipole moment to Rydberg states is around 2000. And the transition dipole moment of the ammonia. So what we do is we prepare the Rydberg atoms in states like this 38S state. And we choose this because the 38S to 38P transition is almost at the same frequency as the inversion intervals in so the transition is ammonia that's also at this frequency, which is around about 24 meters. So in a collision between the atom in this, say, lower Rydberg state here and the molecule in the upper sublevel, the atom can end up getting excited and the molecule can be excited. So we look at this process, we can control it. So here, this interaction arises because of the resonant dipole-dipole interaction. So this has some angular dependence, also that depends on the orientation of the dipoles with respect to each other. At the moment, we don't control the orientation, although we have some kind of post-selection of the Rydberg state populations that allow us to say something about orientation, but that's something in the future that we would like to be better orient the dipoles of both the atom and the molecule. Okay, and then I should say, so this work, like many things in this Rydberg business, goes back to some things that Tom Gallagher and Harry Dunning did in the 70s or 80s. And so this connects to some work that Harry Dunning's group. It's a little bit different. They did experiments where they prepared xenon atoms in Rydberg states. They let them collide with ammonia, let's say zero electric field. They looked at transfer of energy from the rotation of the ammonia molecule to the Rydberg state. So they could see this by doing some electric field ionization methods. So this is a scan where they prepare the Rydberg states in the atom, and then they do a ramped electric field ionization. If there's no ammonia there, they see a single peak ionization signal at the ionization field of the state. If they introduce some ammonia, they see then a range of peaks, different lower ionization field. These correspond to the population of the Rydberg atoms in higher end. From the ionization fields, they can estimate what the values of N are of these excited states. And then they see that the energy intervals between these excited end states and the end state that they started in matches the rotational intervals. And so here there's a transfer of the rotational energy from the ammonia to the electronic excitation. So this is done with thermal samples at low temperature and being zero electric field. So what we've done is we do the experiments now at low temperature, but we can also tune through the resonances using then this transition into ammonia. So the ammonia molecule, so there's these three hydrogen atoms and nitrogen. And there's, if you want to go from this configuration here with the nitrogen above the plane of the three hydrogen atoms to this configuration here with nitrogen below, the hydrogen atoms have to push out a bit as the nitrogen moves through them. So there's a little bit of a barrier to this. That's what's got us here on the hydrogen. So there here is the position of the nitrogen with respect to the plane. If I try to push the nitrogen through here, there's a place where the energy potential resistance increases, and then I get down to this one. So then there's this kind of double well. Because there's a well, then there should be some splitting between symmetric and antisymmetric levels associated with the two states, this up and the down. And these are known as the inversion transition. So the ammonia laser, laser in the 60s, this was then operated on this transition. And it occurs in these lowest rotational vibration states. It occurs at around 8 centimeters per second, about 20. And then the ammonia molecule has a dipole of 1.5, 1.55. So then this is the transition between these states is an electric dipole transition with this kind of transition. Okay, and then we choose helium for mostly some coincidental reasons, but it turns out to be quite well suited to this experiment. So that's reasonably experimentally useful values of N, so that equals 38. The interval from the 38S triplet Rydberg state to the 38P Rydberg state in helium is 0.93 centimeters per second, so 28 gigahertz. So the ammonia interval is 24 gigahertz, and so they're very close to resonance. And if we apply then a small electric field, the start shift brings the bigger start shift from the P state to the S state and brings the two levels closer together as we increase the field. The field is about 5.5 volts per centimeter. This S to P transition of the atom is the same energy as the they happen to be the single system for this case. Okay, so what we aim to do then is to do some collision experiments where we prepare the atoms in the S state and we tune the interaction, the electric field in the interaction and look at energy transfer that we expect to see as a resonance in this kind of field. Okay, so I would say somehow that so there's a connection, say, in other areas of physical chemistry. So in light harvesting complexes, energy is transferred by these dipole-dipole interactions. So there's interest somehow there from looking at dipole-dipole interactions that involve nuclear motion and electronic. The transition of the molecule is a kind of transition of nuclear motion changes, and the transition of the Rydberg atom is not very electronic. And then it's also from this kind of physical chemistry point of view, it's sort of a model system that to look at effects of orientation. And then also here, this ammonia molecule, if it gets inside the Rydberg electron charge distribution, it can interact with the attitude. And so then it's kind of interesting, what we'd like to try to do is to use the dipole-dipole interaction at long range to control whether dipole-dipole interaction is attractive or repulsive. But if the orientation of the two dipoles are parallel, the interaction will be repulsive, but if they're opposite to each other, it will be attractive. And we should expect to see them if it's a repulsive interaction. We shouldn't see this ion molecule reaction because the ammonia won't be able to get in to react with the ion. And if we make it an attractive interaction, then the ammonia might be able to get in and then react with the then there's a connection to experiment with both the co-molecules. And so there have been proposals, so these alkali dimers and things like this, to try to cool them by using sympathetic cooling. And the idea is that you excite the atom into a Rydberg state and exploit the dipole-dipole interaction as a elastic scattering mechanism to then cool by collisions the molecule. So we see proposals to do this. And the same has also had some ideas to do coherent control using the interaction between these atoms in different states and other ground state molecules. This is again in this context of developing molecules and more conceptual development. He has some ideas to use this type of interaction as a way of using the Rydberg atom to non-destructively detect the molecule. Steam, the energy transfer in the Rydberg atom will tell you that there's a molecule there, and so you could just detect the Rydberg atom without destroying the molecule. So there's kind of the connection in some way with these. So to do our experiments, we can use these supersonic beams. And in this case, then we put a small amount of ammonia in the beam. In some experiments, we were doing this like because this one part in 10 to 19 or 10 to 20 of ammonia, it would turn out to be better to have even less ammonia. So we actually now do like 1%. And then the helium atoms we need to excite to Rydberg state. So I'll show you how to do that. We prepare them in this long-lived metastable 2s state. So this is a lifetime of 8,000 seconds. And we prepare them in this state by electric discharge at the exit of the valve. And once this state is populated, this becomes the ground state. So this is already 20 dB above the ground state. And this allows us then the CW laser to go from this metastable state to the Rydberg state. And then we detect the Rydberg states. We don't detect the molecules themselves, so we do the Rydberg atoms, but we do all of our detection on the Rydberg atoms. So we do this by state selected. So the experiment, we have this valve that makes them green, and then we have to just reflect some ions generating discharge. So we have just some fields here to get rid of them. And then atoms and molecules enter into this interaction region where we first excite down to the Rydberg states. And we turn on an electric field with the interaction of the collisions. We leave this on for about 10 microseconds. Then we turn it off, and then we pulse some slowly rising potential on the lower electrode here to ionize the Rydberg atoms and accelerate the electrons to this. Then this transition to helium. So this is this metastable triplet 2s state. So to get to the Rydberg states, then we apply a 2-photon transition with CW laser. So the first transition at 389 nanometers got to 2s to the 3p level. And then from here we can go at 785 to these high Rydberg states. And so these Rydberg states we can do in these nice experiments we can do in a way that we can really control the electric field. So we can use this schema-free scan, this laser that excites the Rydberg states. This is a spectrum which begins at the transition from n equals 3 to n equals 275 and ends at the transition from 3 to about n equals 400. If we zoom in here, we still see peaks in the spectrum. If we fit this, including a small electric field, we can use these very high-end states to determine the magnitude of this great electric field in this type of apparatus, which is around 200 microns. These atoms are really big, so the expectation value of the position operator on the Rydberg electron wave function gives then a radius of the Rydberg electron charge distribution around about 30. The first time I heard that very hard to sustain, including talking in astrophysical spectra, they can see transition of your So then there's some collisions that happen in this beam. And the reason for this is that in the beam there's a small amount of ammonia, and because it's heavier than the helium, it moves more or less at the same speed, but just slightly slower because there's somehow behavior in these kinds of things. So the way we operate the experiment is that we have this pulse of gas that comes out of the valve. We pulse the discharge to make the metastable atoms in the back part of the pulse. The pulse is about 200 microseconds long. In the back, 50 microseconds or so, we apply the pulse. And then the front part of the beam has helium and ground state ammonia, and the back part has metastable helium and ground state helium. And then as the beam moves forward, there's a small velocity difference between the ammonia part and the helium and the metastable helium part. And so the metastable helium, the red part, here moves through the ammonia part of the beam. The relative speed is quite small, so it's about 10 meters. So this this is what gives us our collision energy, and it gives us this low collision energy because it's moving very similar speed. So the collision energy is less than Kelvin. And then I just thought I would tell you something about electric field ionization. So I showed you yesterday about electric field ionization of the hydrogenic Rydberg states. But here we want to do electric field ionization detection of these low L states, and they behave differently. So if we look, for example, this picked at n equals 37. So this is a start map. The energy of a structure is calculated to about the experimental precision all the way to the ionization limit. We do this by diagonalization of the. Here we have to include a basis of states from n equals 28 up to n equals 55 to get the calculations to converge. So there's two sets of limit states here. There's the continuous curves, which are the n equals 0 states, and the dashed ones. So if we excite this n equals 37 state, and if we apply our ionization electric field, it doesn't rise too fast. If it rises in a few hundred nanoseconds, then the state follows adiabatically all of these curves through these avoided crossings. And then ionization occurs here when the energy of the state matches the energy of the saddle point in this potential. And then you can see the P state that we ionize is its n equals 0, also follows all of these curves avoided crossing adiabatically and ionizes them close to the. We were looking at this because we wanted to try to optimize our ionization process. So if I zoom into this region in the box here, so the curves are the calculations, and the points are all measurements that we record by just recording laser excitation spectra, and we see then resonances at each of these positions here. So and this is where we look at versions of the calculator to see that there's some reasonable way towards the measure. So then this dashed red curve here is this S state, so we're interested in one of the states we want to selectively ionize. Near the ionization limits, so this saddle point, which is the black dash curve here, there's an avoided crossing. This we can resolve. So if we zoom in here, because it's just a spectra of this crossing. So we go through that adiabatically. Then the state has a positive star shift. So I told you yesterday when the state has a positive star shift, the electron charge is mostly on the other side of the ion to the saddle charge in the so it's not likely to ionize. So you need the electron to move to the other side of the ion. And this happens at this avoided crossing. And so I'll show you in a second, but if we prepare some atoms to the Rydberg state here and just go slowly through this avoided crossing, once we move the electron to the other side of the ion, which is just in this region here, the ionization suddenly happens with quite a high rate, with a rate that's basically 100% ionization. Okay, so we first do this calculation to know where we are, and then we can do these experiments where we excite the atoms at the position of the star here. And then once we've excited them, we turn on a small pulse electric field that brings them through this avoided crossing. We just scan the amplitude of this field, and we apply different amplitude fields to look at the decay rates on this side of the avoided crossing. So to measure decay rates, we just change the time length for which we need the atoms on the other side of the avoided crossing. So this pulse that brings around the avoided crossing, and then after about 10 microseconds, we then do ionization just to measure the population of what atoms are left in the state. If we do this, then we can measure these decay rates. For instance, these are in different electric fields, so we're switching to slightly different electric fields on this other side of the avoided crossing. Here close to the avoided crossing, or here further away from it. And then we see these decay rates where we lose about an order of magnitude of signal within about a microsecond from the time switch the field. So from these curves, we can measure what we're really measuring here are the tunneling rates of the electron in the ionization process. And if we plot this in this book, it's not so easy to read. So these are the circles here in this lower part of the figure. So you can see it feels around 193 volts per centimeter, which is this place where the electron is now moved to the side of the ion core at the saddle point. The ionization rates go above 10 to the 6 per second. And then interestingly, as we go through this avoided crossing adiabatically and go to this place here where the electron charge is now kind of equally distributed on either side of the ion. And then the ionization rate goes down by the way. Then we can compare to a few things. So this dashed curve here is where you would estimate ionization to happen. And So for us, it happens close, but it's 3 or 4 volts per centimeter below. But only for a state that has the correct location of the electron chunk. And then we can compare to these calculated rates that I showed yesterday for a hydrogenic state that has a similar energetic position. So that's this continuous flat curve here. And this is the kind of closest hydrogenic state we could find. We could then use the yesterday to calculate the. And this is the crosses here in this region. They're a factor of 2 or 3 lower ionization rate than. Then the dashed red and blue curves here are some calculations we can use in complex absorbing potential that are give some idea of what's going on, but not say that all of this work is inspired by work from Joseph Vortex group in Tübingen. So they've done very similar experiments within the frequency domain, so with the widths of resonances in above or around about these ionization fields and extract widths. So this is to give you some confidence in these kind of simple formulas we use for ionization fields, that they're pretty good. They're within a few percent of the kind of fields that ionization happens. But you have to think a little bit about what states you're looking at. The main other thing is that ionization always happens when there's some charge of the electron, or some of the charge being on the side of the ion close to the subatomic. When all of the charges located on the other side of the ion, then very unlikely. That's what happens as it goes through this evolution. Okay, so that was just to connect this to some of these. So then we do this experiment, and by this ionization process, then we can distinguish between the S states with n equals 0, and we can quite easily distinguish between those of the P states with n equals 1. They ionize more like this type again. So if we look at the signal from the P state with n equals 1, then we scan the electric field so through this resonance here, then we can see some population of the P state that occurs then on this place about 5%. Okay, and so this is where we've excited the atoms to the S state with n equals 38. We let them interact for 10 microseconds in the field that we choose. So for example, 4 volts per centimeter, then 5 volts per centimeter. And then we, after this time, the resonance condition agrees very well with what we expect from the extract. The widths, this is a calculation using a kind of impact parameter. I mentioned yesterday, and it's a very reference in the slide because look, it's something that Tom Gallagher had looked at for interactions between different ones. And so the widths are not so in such a way. Then, just to look a little bit more at this, and so we were looking there at this first resonance here, where the transition from the S to P state first comes into resonance. But the blue curve here is the energy of the S state offset by the inversion interval, this 24 gigahertz. So we should expect to see resonances in the energy transfer at all of these different places where this causing power, the resonances to all this transition to all the start states come into resonance. And this is what we see here. So the black points here are the experimental data. And we see each of these resonances, and they have slightly different transition values. They're just where each of these transitions with different start states come into the resonance with the inversion. And then we do a bit more detailed comparison with these calculations. So these are where the cross section for the process depends on the product of the dipole moments, the dipole moment of the atom, and the dipole moment of the molecule. For these range of electric fields, this dipole moment of the molecule is constant. And the only thing that really matters is then we would expect that the resonance widths are proportional to 1 over the square root of this, so 1 over the square root. But these don't agree so well, so we can sort of fit this or the amplitude in some way, but then they don't agree. Weaker resonances here when they agree for the stronger. There's one thing that we can see is in this protection here, we're detecting the population of the S state to the depletion of the S state population. So that's sensitive only to population transfer to the states with n equals 1. So you have to be n. These states with n equals 0 often ionizing more the same as the S. So from this we can see that we can distinguish between this blue curve here where we would expect the transition to the state with n equals 0 to be from the transition that we see, which is the one with a little bit of n selectivity. So that's then to try to shed a bit more light on this disagreement here, we approach this slightly differently. So rather than trying to do a calculation of the cross sections, we just use the calculated Stark shifts to fit the resonances. So the problem here is the Stark shift of each, the transition of each state is different. So we have to do a kind of multi-Gaussian fit where in the frequency domain, the electric field dependence of the EQ is different for each resonance. So we do this using some kind of algorithm process. And these are then the results of this. So this is the n plus 38. You can see we can fit each of these resonances reasonably well and extract resonance widths from this, which are around 200 megahertz. I'll show you on the next slide. Then at n equals 39, the crossing happens in a bit lower fields, and the transition is a bit stronger to the B state. And you can fit this also reasonably well for several of the resonances. And then at n equals 40, the 40S and 40P transition is almost resonant with this inverting interval and only in zero field. So the transition vacuum is very strong. And you see quite a lot of population transfer here. Then these weaker resonances of the transition. So from this fitting process, we can then determine the resonance widths that we measure. And you see that, so from this impact parameter idea, the resonance width should scale with 1 over the square root of the vacuum. It should go down as the vacuum gets bigger. And that's because as the vacuum gets bigger, effectively the interaction time of the molecule with the atom increases. So then, because the interaction time is longer, the resonance is now. But we don't see that. We just see that as the calculated diagram that the transition increases, the resonance width increases most, at least for low transition. So here I've just don't worry about what values of n these are. I just plot them in terms of the transition. So we see then some funny behavior. It's very high, very large transition vacuum. So these are the STP transition. Then equals 40, which is almost in zero field. So this may be that we're actually saturating the transition in some way because the ammonium molecules are in both inversion sublevels, so that you need collision with one that transfers population up, and a collision with another molecule that transfers population down. So this is something we have to look at. What we can tell from this is that the interactions are dominated by, or so the widths are dominated by the interactions and not by the interaction time. So this is something that's then indicates to us that we are in a regime where collision energy is on the scale of the level of interaction. Okay, so that's kind of where we are with this. So we kind of are very much as with things yesterday, doing this from this it's a chemistry perspective where we don't have complete control over the state, but we can do some things where we can select the Rydberg states and do nice detection that allows us to kind of post-select certain things. I should say maybe when I'm here, there are also things happening. So these ammonium molecules are not in a pure rotational state or one of these inversion sublevels. So as we turn on the electric fields here, you can see we immediately see transfer population to other states that are higher in it. So we know roughly what fields they are analyzing. But we just see that as depletion in the population state. And then we just look then at these channels we're interested in where the population is transferring these particular electric fields. This we can get rid of if we can do state selection if we possibly use it. So what we aim to do in the next step is to prepare the ammonia in a state selective way. So we have just one rotational state and one of these inversion sublevels. Then if we do that, we can study effects of orientation of the ammonium molecules in the collision. So the atom, that one is oriented because we apply an electric field in a direction that we know. And this polarizes the atom, so it moves the electron towards the plate of the electrode that we call. We know how the atom that one and we don't have much control. And then also we want to look at effects of higher order multiple interactions. We expect that there will be strong effects of quadrupole interactions. See if we look for a particular delta m, if delta n equals 2. This is work that we are aware of from Christiana Koch's group in Berlin. So they've done calculations of these kinds of energy transfers, and they see that quadrupole interactions. So this is what I wanted to tell you about. So this work initially with the experiments with warm or room temperature ammonia that was done by balancing the shoulder, and then Claudio Gabos. Where we looked at the resonance widths for the range of Rydberg states that have been doing. So I mean, well, what we can do is we can. So there's better calculations. So what we do is that, like, we extract something return, we do a fit. That's all we do. That gives us this part and then we want to see that this makes sense, that it should be on this scale. So for that, then we have looked at this. So this, you can write down an expression for this interaction that arises because of this distance dependent or the intermediation dependence of the defect or of the interaction derivative electron with the dipole. And so from this, so this is something that's kind of a physical. And so everything in this we know. So that's what we've done. And if we do that, then we also get the same kind of scale. The problem is that you can look in the question is whether it's sensible to look at interaction very weak. I mean, if you want to say study the interaction in detail, it's probably better to study it in place where the interaction is very strong, so closer to this level. And that's what was done in these experiments where we needed the resonance with the information. The interesting thing for us is that you think that if you make these very long derivative states of multiple, these types of effects wouldn't play very big role. They would be dominated by. And that's, I think, the interesting thing for us is that if you want to worry about how these derivative states behave, you have to do some treatment things. So I think that's where the things we've learned from the so yeah, that's right. So we've just, I mean, we say we can calculate fluorescence like that, and then we have everything else gathered together. And look at it, they're small contributions. Or it's even but yeah, it's all bunched together that there can be this automatization or some fluorescence at this lower. I think from the previous measurements, I mean, resonance that it's all just bunched together. So we that's maybe interesting is to try to do something where you then look at the products of the decay. We just look at what's left in the chunk. And if you can look at, say, the dissociation products of the seed to distinguish whether it's polarization, so that would maybe that's maybe something that, yeah, it's good to kind of wait to do that. Yeah, yeah, well, it's a bit less than 100. It's behind. Yeah. Thanks.
10-minute break. Nice. Thanks. I will immediately pick up on the energy transfer in my talk now.
Ah, right. Yeah, that's good. At least I'll stay at the two.
Yeah.
Just turn it off.
Yeah, but I need this. Okay, so I need this adapter from Chris. Yeah, I'm still having a hard time.